In this video, we're going to define the idea of an integral domain and give some examples. So before we get started, I just want to mention what the word integral means here. So what we're going to find after we define what an integral domain is, then an integral domain is a ring that in a certain sense is like the integers. That's what the word integral means there. It's a ring that is like the integers in two really crucial ways. One of those ways is that the ring is going to be commutative. So part of what it means to be an integral domain is that it's a commutative ring. Multiplication is commutative. The other way it's like the integers is that there are no zero divisors, but we need to say what a zero divisor is. So we're going to make the following definition. So definition, let R be a commutative ring. And let X be a non-zero element of the ring, so not the additive identity. We say X is a zero divisor of R if there exists some Y in R such that Y is non-zero and X times Y is 0. Okay, so X is a zero divisor if it's non-zero and there's some other non-zero element such that the product of those two elements is 0. Okay, so part of why we call it a zero divisor is that if you read this equation, one way you can think of this is you can say X divides 0. If we define the term divides in a general ring and not just the integers, this is kind of like saying that X divides 0. So it's a divisor of 0. Here's an example. Let's let R be the ring Z mod 10, and that's a commutative ring. So we're only ever going to talk about zero divisors in the setting of a commutative ring. So let's take X to be equal to 2. Again, that's 2 in Z mod 10. Is there some element of Z mod 10, some non-zero element that can be multiplied by 2 that would give me 0? In mod 10. Well, when I think 0 mod 10, that's multiples of 10. So what if I let Y equal 5? Okay, so X and Y are both non-zero, but X times Y is equal to 0. So this means that 2 is a zero divisor of Z mod 10. But this means something else too, which is that 5 is also a zero divisor. Why is 5 a zero divisor of Z mod 10? Well, there is a non-zero element, namely 2, that can be multiplied by 5 to give 0, because if 2 times 5 equals 0, then 5 times 2 is also 0. R is commutative. So 2 and 5 are both zero divisors. And we can find other zero divisors as well. 4 would be a zero divisor, 6 is a zero divisor, 8 is a zero divisor, because any of these times 5 would equal 0. So 2, 4, 6, and 8 are zero divisors, so is 5. And I think those are the only ones. So anyway, that's the basic idea of a zero divisor. Now we're ready to define what an integral domain is. So here's the definition of that. A ring, R, is an integral domain if it is commutative and has no zero divisors. Okay, so for example, Z mod 10 is not an integral domain. It's commutative, it satisfies that property, but it has zero divisors, and that rules it out of being an integral domain. To be an integral domain, you got to have no zero divisors. So a couple of examples. Z is an integral domain. That's what we were talking about earlier. An integral domain is sort of designed, in terms of its definition, to be like the integers. Z is an integral domain because it's commutative. And if you just think about two numbers, X and Y, in the integers, X and Y belonging to Z, then X has to equal 0 or Y has to equal 0. Okay, so what that means is that if I have two integers whose product is 0, one of them's got to be 0. And for us to have zero divisors, we have to have two numbers, both non-zero, that multiply to 0. Okay, so this statement here means that there are no zero divisors. So that's one example. Z is an integral domain. Also, integral domains for basically the same reason. The ring of rational numbers is an integral domain. So is R. So is the ring of complex numbers. All of these are integral domains because they have this property over here, which we call the zero product property. Because they satisfy the zero product property, they can't have any zero divisors. Actually, that's true of the rationals, the reals, and the complex numbers. You can prove it for those for a slightly different reason than you can for the integers. And I'm going to do that now, just because it's kind of a nice generalization. So here's another example. One thing that these three rings have in common is that they're all fields. Again, just as a reminder, a field is a ring that's commutative. And every non-zero element has a multiplicative inverse. And we can show that anytime those two conditions are met, anytime we have a field, that's going to be an integral domain. We're going to have no zero divisors. Any field F is an integral domain. Here's the proof. Let F be a field, and let X in the field be non-zero, and assume X times Y is equal to 0. Okay, we're going to show that Y has to be 0. Because if we can show that, xy being equal to 0 implies that y is 0, then that means that there's no way for x and y to both be non-zero and have the product come out 0. That would mean that x can't be a zero divisor. So the way we're going to show that is we're going to say, let's start by assuming xy equals 0. We've assumed that. So since xy equals 0, we can multiply both sides by a multiplicative inverse of x, since we assumed x is non-zero, and we're in a field, therefore x has a multiplicative inverse. This gives us x inverse xy equals x inverse times 0. Well, x inverse times x is 1, so that means that 1 times y equals x inverse times 0. And we have a property of multiplication that says that anything times 0 is 0. And of course, 1 is the multiplicative identity. So this means that y has to be 0, which is what we wanted to show. So x is not a zero divisor, because the only way to multiply x by some element of the field and get 0 is to multiply it by 0. All right, well, x was anything non-zero in F, so F has no zero divisors. So since it's also commutative, F is an integral domain. And sometimes we'll abbreviate that by saying ID. F is an integral domain. All right, and that's the proof. So any field is an integral domain. But I do want to point out, because, for example, Z is not a field, the integers typically don't have multiplicative inverses. A couple of them do, but most don't. It is possible to be an integral domain without being a field. So being a field implies being an integral domain, but not the other way around. Okay, here's one more interesting non-example. If R and S are rings, and neither one has to be a subring of the other, they're just separate rings, then we can define the direct sum R plus S And this is going to be kind of like a direct product for groups. The direct sum R plus S to be the set of all order pairs R and S, where R comes from R and S comes from S, and the operations R1 S1 plus R2 S2 equals R1 plus R2 S1 plus S2. So we just add in each coordinate. And then here's how we define multiplication. R1 S1 times R2 S2 is equal to R1 R2 S1 S2, just multiplying each coordinate. So it's sort of the most obvious, and I'm using the word obvious in quotation marks there, the most obvious operation you could come up with for ordered pairs. Nothing fancy going on there. Now, first of all, I claim that the direct sum is a ring. To prove that would take a little while. It would just be checking a lot of properties, so I'm not going to do that in this video, but it is a ring. But I claim that it's usually not going to be an integral domain. Specifically, if R and S are both commutative rings with unity, then we can observe the following. We can take this element, 1, 0. This is the multiplicative identity from R, and this is the additive identity from S. That's a non-zero element of the direct sum. The direct sum has only one zero element, and that's 0, 0. So this is non-zero. I can multiply that by this element, 0 from R, and then 1 from S. And what do I get? Well, I get, in the R coordinate, I get 1R, that is the multiplicative identity from R, times 0 from R. And in the second coordinate, the S coordinate, I get 0 from S times 1 from S. And that gives me 0R, 0S, which is equal to the 0 element of R plus S. So in other words, I've got two non-zero elements here that multiply to the 0 element of R plus S. That means these are zero divisors. And if I have zero divisors, then I'm not an integral domain. R plus S is not an integral domain. So those are just a few examples and non-examples.